So again, in Lab 7, we're going to start out with some simulations. So you go into the Physics 1100 folder, and you want to go into the Lab 7 folder. And there's 3 collisions in here, and we're going to look at all 3 of them. So double-click to open up the first one. And in your report, you're going to screen capture the collision both before and after the collision, so after we've run the simulation, and paste those into your report. Another thing you need to do is you'll need to write down some stuff right now. So you want to write down the mass and the velocity of the first ball before the collision, and the mass and the velocity of the second ball before the collision. And then you're going to calculate the momentum of the first ball before the collision and the momentum of the second ball before the collision. Then you'll run the simulation by clicking the Run button, and after they've collided, you can stop it too. And then here again, you'll want to take a screen capture, and you want to write down the mass and the velocity of the first ball after the collision and the mass and the velocity of the second ball after the collision. So once you've got all your data and have calculated your values, then you can move on to the second simulation. So I'll close this down and open the second collision. And in this one, you'll notice that the balls are headed towards each other. So one of them has a velocity pointed in the positive direction and the other has a velocity pointed in the negative direction. Again, write down the mass and the velocity of the first ball before the collision, the mass and the velocity of the second ball before the collision. And here's one thing to pay attention to. Remember that velocity is a vector. It's got a direction. That means that momentum is also a vector. You need to keep track of minus signs. So when the velocity is pointed in the negative direction, write it down with a negative sign. If you don't keep track of the minus signs, you won't be able to show conservation of momentum later. So you grab the data that you need before the collision, take your screen capture, and then you'll run the simulation and stop it after the collision. And again, write down the mass and the velocity of the first ball after the collision, the mass and velocity of the second ball after the collision, keeping track of the minus sign on the velocity that's negative, and then you'll calculate the momentum of the first ball after the collision and the second ball after the collision, and take your screen capture. Then you can move on to the third simulation. So again, close this. If it asks you to save changes, say no like usual, and open up the third collision. And in this one again, they're pointed towards each other, so make sure you keep track of the minus sign on the velocity that's negative. Write down the mass and velocity of the first ball before the collision, mass and velocity of the second ball before the collision, run the simulation, and in this case they just stop, so they stick together and don't go off anywhere afterwards. Again, write down the mass and velocity of the first ball after the collision and the mass and velocity of the second ball after the collision. Then calculate their momentums. And then you're done with this third simulation. Now, before I show you the equipment for Lab 7, I do want to point out something that's true in the lab manual for Lab 7, and that is that when they tell you to summarize your results in a well-titled table, for the first time ever, they don't give you the table. You're expected to create that yourself. Likewise, for the conclusion, it doesn't give you that bullet list of things that should go into your conclusion anymore. You're expected to know how to write a conclusion by now and to do it on your own going forward. So this is going to be true for the rest of the semesters, that you'll be writing your own conclusions and creating your own tables without any extra help. It's important you know this now because this is also going to be true for the lab exam, which is your next lab, is you'll have to write your own conclusion without a bullet list. Now you are allowed to have a formula sheet in the lab exam, so if you wanted to put the bullet list on that, you could, but just be aware it won't be there by default. I have put an information video up about the lab exam and what you should do to prepare for it. So I recommend you watch that a little bit early so that if you've got any questions, you can find your lab instructor and ask them. So now we're going to talk about how you do the experiment. So first of all, you're going to need to weigh your 2 carts. So there's cart 1 and cart 2. Cart 1 is the one that's closer to the sensor. So you would weigh cart 1, and then separately you weigh cart 2, and then you want to weigh them together. So you just stack them like this and weigh them as one big chunk like that. And we're weighing them together so that we know what the uncertainty of the total mass is without having to do a calculation. The second thing you want to do, and I know I'm always harping on you guys to do this, but you want to level the track very carefully with this experiment. So this is one experiment where if you don't level the track, it can make a big difference to whether or not you get good agreement between your 2 values. So do that as carefully as you can. Now we're going to be studying an inelastic collision. So these cars have Velcro pads on them and they stick together. So the experiment that we're going to run is we're going to start one cart sort of in the middle of the track, the other one at the edge of the dead zone. We'll run them together they'll stick and continue down the track together. So that's an inelastic collision, a sticky collision. So an elastic collision is a bouncy collision, so when things bounce apart. An inelastic collision like this is when they stick together. Now theoretically, in an elastic collision, so a bouncy collision, both momentum and kinetic energy are conserved. Theoretically, in an inelastic collision like we're studying, momentum is still going to be conserved, but kinetic energy will not be. And you can kind of understand why that would be if you think about two balls of putty. If you throw them together, they go splut and they stick and they deform. Some of the energy of deforming the putty gets lost to the collision. So that's why kinetic energy is not conserved in a sticky collision. And to a very minor extent, the same thing's going on with these Velcro hooks. They hook and they kind of flex, and we lose a little bit of energy to that. We also lose a bit of energy to the sound they make when they crunch together, but that can happen in an elastic collision also. So again, theoretically, in this collision that we're studying, we expect momentum to be conserved, but kinetic energy not to be conserved. So the way in which we take data with this is, like I said, we put one of these cars about 2/3 of the way down the track. The other one starts at the edge of the dead zone. And I'll show you on screen how to take data with this in a moment. But you would start your program running, and then you'll send this one down the track. They collide, they roll off together. The quantities that you're going to need to be calculating later are momentum and kinetic energy for both of the carts, both before and after the collision. So because you have the masses already, what you actually need to get from this experiment are the velocities before and after the collision. So I'm going to show you now on screen how you get the velocities before and after the collision using the velocity program. So open up the 1100 folder, and we have been using the acceleration program a lot this semester, but the velocity program works better for this experiment. It's got a bigger position time graph. So open up the velocity program, and then you would also want to set up your carts ready for the collision. And then you would click Collect, and send the one cart down the track to collide with the second one, and then they roll off together. And that gives you a graph that looks like this. Now, just so you know, this stuff here is the bounce back at the end of the track. We actually don't care about this area at all. What we care about is this little bend in the data right here. So this is when the collision took place. So let me expand this graph a little so we can see that better. So what we're looking at here is that this linear area right here is when the one cart was rolling down the track by itself. And then the collision happened at the bend, and then the two carts rolled off together, slightly slower, because now the rolling mass is heavier. So that's in keeping with conservation of momentum. Now we want the velocity right before the collision and right after the collision. And of course, on a position time graph, to get velocity, you want the slope of the line. So you could highlight the linear section here and get the slope of that. However, there's something we should do here in order to get the best possible data. It may not be easy to see, but there's a little bit of friction on the track, and that can affect our velocity values. So to get the best agreement between your two values, highlight just a small amount of data right before the collision and fit your straight line through it. And then again, highlight just a small amount of data right after the collision and fit that too. So rather than highlighting the whole area and getting a fit of everything that looks basically linear, just choose a small amount of data right before and right after the collision, and that should give you the best agreement between your values. So this would be the graph that you want to paste into your report, because it shows you the velocity of the single cart before the collision and the velocity of the two carts together after the collision.